Welcome. The topic for our project is Celestra, which is NVM-aware compute in memory LDPC error-correcting code architecture for STT-MRAM-based memory systems. My name is Souhardya Bose. I, along with my friend Ridhiman Maiti, has contributed to this particular project. Let us look into the motivation behind this project. STT-MTJs, being a non-volatile memory, serve as an important candidate for last-level cache and main memory due to its very low leakage, high endurance, and very fast access time. However, due to aggressive technology scaling, we have very high bit error rates of the order of 10 to the power minus 5. But system level targets demand word error rate to be less than 10 to the power minus 12. Therefore, we require very prominent error correcting codes in order to work with these devices. The most popular being the low density parity check, which is the LDPC error correcting code. Traditional LDPC encoder decoders have been implemented as digital engines at the memory controller. However, they have very high energy and latency bottleneck due to heavy data movement between the memory array and the decoder logic. In this particular work, we propose Celestra, which is a compute-in-memory assisted LDPC error-correcting code architecture in order to deal with this non-volatile memory devices. In this particular case, we were looking into MRAM-based memory systems. In this particular case, Celestra, the LDPC parity check matrix is mapped onto an on-chip SRAM-based digital compute-in-memory macro that performs key parity and message passing operations near the memory, thereby significantly reducing the data movement. So let us now look into the error matrices of this particular devices. So STT-MRAM can have multiple error sources. The first one is the read disturb errors. So when we have repeated read operations, then there can be some erroneous bit flips due to very low magnetic anisotropy or the low TMR of these devices. The second one is the process variation induced failures. The variation in the STT MTJ dimensions and the transistor parameters can increase the susceptibility to sensing and the switching errors. The third one is the retention failures, where the stored magnetic states gradually drift over very long ideal periods. The fourth one is the write failure, where the write current can be insufficient in order to switch the state of the MTJ reliably. The fifth one is the thermal fluctuation, where the MTJ state can also switch because of the thermal fluctuations in the free layer. So when the thermal fluctuations in the free layer is greater than Kb times T, then the MTJ state can switch from one state to the another. Now, let us look into the channel modeling, how we mathematically model the channel in this particular work. So in this particular work, we have modeled the channel as a binary symmetric channel. So here we have two operations. The first one is the write operation, where we write into these devices, and the second operation is the read operation, where we read from these particular devices. So the error can happen in two ways, which is denoted by 1 and 2 in the diagram on the right. The first one is that when we do the write operation on these devices, the state of the MTJ can flip from 0 to 1, and the probability of this bit flip is denoted by P write. During the read operation, there may not be any bit flip and we get the accurate value. So therefore, the 1 gives you 1, which is denoted by 1 minus p read. So overall, from write operation to read operation, we are having an error where we wanted to write 0, but ultimately we are getting 1. So in this particular case, the error is actually given by p write into 1 minus p read. Similarly, we have the other error where the error can be given as 1 minus p write into p read. So the effective probability of error can be determined as p read into 1 minus p write plus p write into 1 minus p read, where p read denotes the probability of the read error bit flip and p write denotes the probability of write error bit flip.
Hello. LDVC can be a very powerful code to correct multi-bit error in STT-MRAM, which happens due to bitwise read-write failure of STT-MRAM. LDPC is a very hardware-friendly algorithm because it requires just GF2 MVM for encoding and decoding. In GF2 MVM, I mean, in GF2, multiplication is just bitwise and addition is just bitwise OR. So it is very hardware friendly to implement. Few previous works have already done it in FPGA using digital computation hardware. However, for LDPC, we have to multiply our message bit or code bit with a specific with a unique vector. To get that vector, we need frequent read access from our SRAM. So that creates a bottleneck for data movement, and this motivates us to investigate on near memory or in memory acceleration of LDPC. this is our NVM aware computing memory hardware architecture for LDPC encoding and decoding. In this architecture, initially we get the message from our on-chip processor, uh, and we encode that message U by multiplying uh, with a binary matrix G in GF2 to get the code word C. Um, the GF2 multiplication is going to be implemented by a uh, SRAM based DC matrix vector multiplication array. That MVM will happen in GF2. That means here the multiplication is bitwise and addition is bitwise XOR. So it is going to be implemented by just and followed pixel wise and followed by a XOR tree. In this way, we get the code word C. The code word is going to be written into the STT-MRAM memory array. During writing the code word, it will pass through a write error channel, uh, which will be modeling the write error of STT-MRAM. After that, when we read the data again from the STT-MRAM, some read error also can happen. After two level of corruption due to read and write of the code word, finally we receive R as our code word, our received code word, and um, that R is going to be multiplied with another binary matrix H to get the syndrome vector. After getting the syndrome vector, that vector is going to be multiplied by the pseudo inverse vector, pseudo inverse matrix of H to get the estimated error vector by which our initial code word might have been corrupted to. Uh, now we can add our estimated error vector with our received vector to get the corrected code. From the corrected code, we can discard our parity bit because uh, the for on-chip processing we just need the message, not any parity bit. Or in hardware we can actually uh, neglect computing the parity bit. We can just compute the message bits and pass it to the on-chip processor for processing. Now we're going to see the performance evaluation of the encoder. The encoder is just a matrix vector multiplication in GF2. The G matrix of the encoder has to be mapped into many SRAM macros, and output of them has to be uh, reduced using is XOR tree. If the crossbar size is less, the XOR tree dimension would be more. If crossbar size is larger, then the XOR tree depth will be less. So we can see that trend here. As we increase the crossbar size, the XOR tree length is decreasing and XOR tree latency is also decreasing, but the crossbar is the XOR tree inside the crossbar is larger for larger crossbar. So the crossbar is uh, taking more time to compute in case of large arrays. Yeah. And we have used message length of 4096 to get that data. Mm. For encoder power, the main contribution comes due to the XOR MVM and the XOR all reduce operation takes insignificant power as compared to it. And as we increase the code size, the energy is increasing linearly, and as we increase the crossbar size, the energy is almost same. And in case of throughput, in throughput, we have compared the throughput when the architecture is pipelined and when it is not pipelined. But in case of encoder, there is a single operation and which is happening in all parallel. So the throughput is same in case of pipeline and non-pipeline.
So let us now look into the performance evaluation of the decoder. Inside the decoder, we have two operations happening one after the other. The first one is the computation of the syndrome, which is shown by the blue color in this figure. The second one is the computation of the estimated error, which is shown by green color. It is denoted by back projection in all these figures. In between these two operations, we have the all reduce operation, where the orange color denotes the all reduce operation between multiple syndrome tiles and the red color denotes the all reduce operations between multiple back projection tiles. Finally, we have the bitwise OR operations between the estimated error and the received code word into the decoder unit. And this has been demonstrated by purple color in all the figures. So let us now first look into the latency analysis of the decoder. Here in all these figures, the y-axis denotes the latency in nanoseconds and the x-axis denotes the code word dimensions. Here, the code word size have been increased, keeping the message bit to be fixed, and we have increased the number of parity bits. In this latency analysis, we have seen that when we are doing the syndrome computation, the total latency is constant even if we increase the code word size. This is because we have provided sufficient number of computing memory units in order to do the syndrome computations. And all these operations happen parallelly. So even if we increase the code word size, since all the bits have been mapped to these in-memory compute units and all the operations are happening parallelly, the total latency is constant even if we increase the code word dimensions. But in the other case, when we are doing the back projection units, the depth of the ZOR is actually directly proportional to the parity bits, and we have increased the number of parity bits. Therefore, the latency increases linearly when we increase the code word dimension. So here it can be seen that we have linear increase in latency when we increase the code word dimensions. And finally, we have the bitwise OR operations latency, which is denoted by this purple color. So here the three plots denotes the overall latency when we do the computations across different crossbar dimensions. The first one is 128, the second one is 256, and the third one is 512. Next, we move into the power plots of the decoder. So here, the most of the power is actually taken by the syndrome computation and the back projection computation, which is happening in memory. So here we can see that as we increase the number of code word dimensions, here the power increases linearly. This is because when we increase the number of code word computations, when we increase the number of code word bits, then more number of bits are actually mapped into the crossbars. We require higher number of crossbars and therefore the power increases linearly. Next, we move into the throughput of the decoder, where we perform the throughput analysis in two cases. The first one is the pipeline version, and the second one is the non-pipeline version. So here we can see that the pipeline version offers much higher throughput compared to the non-pipeline version in all the cases. Now let us look into the result analysis of our work. Here we have compared our work against different state-of-the-art work where they have actually implemented the LDPC encoder-decoder scheme on real hardware. So here we have compared our work against them in terms of latency and throughput. The plot in the bottom shows the result of the bit error rate after the LDPC decoding. So the y-axis denotes the bit error rate after LDPC decode and the x-axis denotes the code rate. So here it can be observed that we are being able to achieve substantially low bit error rate after LDPC decoding. It is worthwhile to mention that we would require a very large Monte Carlo simulation with large number of samples in orders of billions in order to demonstrate that the LDPC can meet system level bit error rate to be less than 10 to the power minus 12. Now, the conclusion of this work. Celestra provides a framework for non-volatile memory aware compute in memory LDPC error correcting code for STT-MRAM based devices. It provides a co-design of the decoder plus the STT-MRAM error model and also the message passing into the SRAM based compute in memory units. We have been able to cut the energy and latency while keeping the post error correcting code bit error rate to be in the acceptable range. Overall, the Celestra provides the architecture, channel modeling, and also the compute in memory based decoder, and also the latency and energy model in this particular work. In terms of the future work, we can explore larger and more realistic LDPC decodes across wider code range. We can also explore adaptive error correcting codes across time varying raw bit error rates. Furthermore, we can also explore joint optimization of the MRAM operating conditions plus the Celestra parameters in order to achieve system level efficiency. Thank you.